All right, thanks for coming. Welcome to Fermilab. As you said, I'm going to be talking about neutrinos, which tell us rather a lot about the universe, sort of a surprising amount, I would say. And the first question you probably want to have is, why are you talking to a particle physicist instead of an astronomer? I'm willing to bet a lot of people in this room probably know more about astronomy than I do. But what I do know about is neutrinos. And those neutrinos can tell us a lot about what's happening sort of in astronomical bodies as close as our sun, or as far away as distant, extremely powerful galaxies. So let me start with a little bit of history on the neutrino itself, and we'll come back around to what it has to do with astronomy in a little bit. So the neutrino itself was introduced to solve a problem. And that problem was that in the early 20th century, people were making measurements, specifically this guy named James Chadwick, was making measurements of nuclear decay. And what he was finding was that when he looked at the energy coming out of those decays, he wasn't getting all the energy out he expected. Right? And the worry was, at the time, that maybe conservation of energy is just not true on a subatomic level. But this is a really controversial statement at the time. This is one of the fundamental laws of physics. And the solution that was proposed was to introduce a new particle that was neutral and interacted so weakly you could never see it. Right? So this is a very controversial thing at the time. Right? They've introduced a particle that they thought no one would ever be able to measure. And that was introduced by Wolfgang Pauli to solve this problem. Actually, at the time, it was called the neutron, because the neutron had not yet been discovered, also by this guy, James Chadwick. And it was first really put into theory, and someone made a sense of what the neutrino could be, was Enrico Fermi, who's, of course, the person this laboratory is named after. Right? Of course, it didn't go on being undetected, though it did take something like 30 years from after Fermi's theory to be able to really measure it in an experiment. And that was these two guys, James Reines and Cohen, who measured neutrinos coming from a nuclear reactor and detected them in this experimental setup you see over here. The neutrino would come and interact in this water segment over here, and then these sections around it were made up of scintillator, which is material that emits light when charged particles pass through it. It's one of the common techniques we use to try and observe particles, and it'll come back later. So these guys in 1956 first observed the neutrino, right? And the neutrino then becomes just a member of the family of subatomic particles, right, that make up the standard model of particle physics. They come in three flavors: the nu-e, the nu-mu, and the tau. And in the original theory, they didn't have any mass, right? They were believed to be totally massless, weakly interacting particles. So what do I mean when they say they only interact weakly, right? So when I say they only have weak interactions. So in particle physics, when we talk about the strength of an interaction, what we're really talking about is what we would call a cross-section, which basically just means how often the particle interacts when it passes through matter. Right? And it turns out that neutrinos interact very, very weakly, which means they interact very infrequently. Right? So you may have heard of alpha, beta, and gamma radiation, right? That alpha is stopped by something as thin as a sheet of paper, but gamma radiation will even pass through a thin amount of lead, right? So that's a high-energy photon, the kind of thing you see coming from, in telescopes. And a high-energy photon will get through about 20 centimeters of carbon, which is a not-so-dense material. By comparison, in order to stop a neutrino, it on average has to go through a light year of lead, right? Which is an enormous amount of material, right? So these are very weakly interacting, which means they interact very, very rarely. In fact, there's billions of them passing through us, coming from the sun, having passed through the Earth already, and they just keep on going, off into the universe. So this is, in some sense, a blessing, right? So this means that the neutrinos can escape from really dense areas and tell us about what's happening inside of astronomical bodies, right? So there are neutrinos that are coming from the center of the sun and pass right out of it, right? Compared to light, which sometimes can take many thousands of years, maybe it's tens of thousands of years. It's a surprisingly long time for light to get out of the center of the sun and be able to reach us. But the neutrinos just pass right out almost instantly. The downside, of course, is that once those neutrinos get to Earth, most of them pass right through the Earth and just completely avoid our detectors. So that means that they have a lot of great information, but they're really hard to spot and to try and do something with. Right? So how do we see the neutrinos? Right? So the first point is that you can never really see a neutrino. Because what do you mean when you say you see something? Right? You see something by having a photon bounce off of it and come into your eye or into your detector. But photons only interact with material that has an electric charge. So they just don't interact with neutrinos. You literally can't see them. What you can do, however, is take that neutrino and let it interact with an atom, in this case an argon atom. And when that neutrino interacts, it'll break up that atom or nucleus or nucleon, right, and emit charged particles, which you can see in our detectors. So this is what we're usually doing when we talk about seeing neutrinos or measuring neutrinos. What we're doing is letting the neutrinos interact in our detector and then seeing what comes out of those interactions. So where do we get neutrinos from? We'll come back to how we detect them in a little bit. So there's a bunch of man-made sources of neutrinos, right? So as I said, Reinus and Cowan used neutrinos that came from a nuclear reactor, which is a very copious producer of neutrinos. We also can make them in accelerators, like here at Fermilab, as we was mentioning in our introduction. And you also get tons and tons of neutrinos from nuclear weapons. There was an early idea to try and detect neutrinos before the neutrino had been observed, try and put a detector deep underground near a nuclear test explosion, which would have been really rough on that poor graduate student. This actually comes from a XKCD article about neutrinos, which if you haven't read it is quite good, highly recommended. But there are also astrophysical analogs of these man-made sources, right? So the sun, in many ways, is a nuclear reactor, not so dissimilar to what we have. It's fusion instead of fission. But we're getting neutrinos from nuclear reactors. You get neutrinos from explosions in space, like supernovae, and you can also get them from cosmic accelerators. And so I'm going to talk about these three sources of neutrinos and what the neutrinos that come from them can tell us about the universe. So we're going to start with the sun, because it's the closest. The neutrinos are the lowest energy. So this is the sun as it looks in photons. And this is the sun as it looks in neutrinos, as measured by the Super Kamiokande detector. So that seems really impressive, until I tell you, of course, that the actual size of the sun in this image is the size of one pixel in the middle. The neutrinos are not a very high resolution detecting material, but they can tell us a lot about what's coming from the inside. Right. So the neutrinos that come from the sun, as I said, come from nuclear fusion reactions. So this is an example, right, of one of those reactions. You can see that in this chain of getting from hydrogen into helium, you emit a couple of neutrinos from these early interactions. And so what that means is that the rate of neutrinos that come from the sun tells us about the rate that these fusion interactions, these fusion processes are happening at. Right, and the rate that those fusion processes are happening at, those define the temperature of the sun. Right, so this, as you can imagine, is a very interesting question to try and answer. How hot is it in the center of the sun? And neutrinos can tell us that. And it turns out that when I say the flux of neutrinos, that's how many neutrinos are coming per second into an area on the Earth. Right, so how many neutrinos we're getting from the sun is a very sensitive measure of the temperature inside the sun. For some of the processes, it goes as a factor of 10 to the 25. So that's a really big exponent. So what that means is that getting 10% less neutrinos means that the sun's temperature is 93% lower. Right, so this is a very precise measure. Do you have a question? No. Of what's happening in the sun. So not that long after neutrinos were discovered, a guy named Ray Davis said, you know what, we should try and measure this flux of neutrinos because it's going to tell us all this interesting stuff about astrophysics. So they set up this detector in the Homestake mine in South Dakota. It's actually the mine from the show Deadwood, if you've ever seen that. Right? It's very near that town. Sets up this detector underground, basically full of dry cleaning fluid, and looks for a neutrino to come in and transform a chlorine atom into a different atom and try and detect it. I think it's barium, something like that. Huh? Argon. There we go. So he sets up his detector, waits around, sees what happens. And what he finds, when he turns this detector on, he gets significantly fewer neutrinos than he was expecting. Right? So the standard solar models, this guy named Ray Bacall, comes up with this model of how many neutrinos you expect to see given the sun's temperature, and expects a number of 8 in this extremely precise unit called the solar neutrino unit. Right? Expects 8, and what you actually observe in the detector is 2 to 3. Right? And this measurement goes on for 20 years here. You see these data points bouncing around. You see you're getting a number, observing a flux of neutrinos about a third of what was being expected. Right? So this sets off a decades-long search. Or as I said, this plot's going up until the 90s. Right? There's a bunch of other experiments that come along that try and measure the neutrino flux from the sun in various ways, and they keep coming out really low. And how low it comes out depends a little bit on what technique you're using, what atom you interact with. But they all agree the flux of neutrinos is just not nearly high enough, right? And so this leads a lot of people to doubt this standard solar model, causes a lot of controversy. But it turns out that what's happening here is not that we have the sun wrong, that we had neutrinos wrong, right? What the low flux of neutrinos was telling us was actually that the neutrinos were oscillating, which is that they were changing from one flavor of neutrino to a different flavor of neutrino as they traveled from the sun to the Earth, right? So these detectors were mostly just sensitive to electron neutrinos, right? So just that one particular flavor. And so a bunch of those were missing. The reason they were missing, as I said, is they were changing flavors along the way. So this problem was sorted out in 1998 by this experiment called Super-Kamiokande. It's one of these experiments I worked on when I was in Japan. Where they figured it out by seeing that the flux of muon neutrinos coming from the bottom of the Earth, coming from a long way, was much smaller than the ones coming from the top of the Earth. So it tells us that as the neutrinos traveled a longer distance, some fraction of them oscillated away. So this used actually not solar neutrinos. It used atmospheric neutrinos, which come when cosmic rays collide with the atmosphere. But it's, the physics of what's happening here is the same. So this is actually a scan of a transparency given by Takaaki Kajita in 1998, who just last year was given the Nobel Prize, along with Art McDonald, for discovering this process, for solving the solar neutrino problem and discovering neutrino oscillations. Right. So these neutrinos that came from the sun, it turns out we had the solar model right all along, right? That we had the temperature of the sun right from neutrinos. Launched this whole field of study that these guys were awarded a Nobel Prize for, and started a whole series of experiments to try and study neutrino oscillations in greater detail. And these are three that happen to be here at Fermilab that study this, right? So there's the Minos detector. These two are actually the FAR detectors, which are in northern Minnesota. And then the Dune experiment, which is not yet built, but we're trying to build, which is also going to go into the Homestake Mine in South Dakota, that same place that Ray Davis did his solar neutrino experiment. I picked these three because these are the ones I worked on. I have an especially soft spot in my heart for this guy, since that was what I did my PhD thesis on. But so it's launched this whole field of trying to study what's happening with the neutrino, right? It became the first evidence of physics beyond the standard model, right? It became very interesting for us particle physicists, right? But but from your perspective, what the neutrinos are telling you is that we know the temperature of the inside of the sun. So problem solved. Let's move on to supernovas. So supernovas, I'm sure you all know, but as I put just in case, right? It means an energetic outburst resulting in the disruption of a star. So I say this very technical definition to make clear the point that what we observe, right, is a big burst of energy, and then the star is no longer there, or is different after that burst is done, right? And while that supernova is going on, the supernova itself can be as bright as the whole galaxy it's containing, right? Which is a really remarkable outburst of energy lasting a very short period of time. So this is a really interesting thing that we want to try and understand better. The trouble is that the information we have is pretty limited, right? If all we're doing is looking over here and seeing a bright light. So I can tell you a little bit. Right, the supernova we're going to talk about here, specifically called Type 2 supernova, which are, these we think come from gravitational collapse. I say we think because what we actually know is that Type 2 supernova have H lines in the spectrum, and they create compact remnants. That means a neutron star or a black hole, some very dense collection of matter, and they produce lots and lots of neutrinos. That's what we observe, right? Those are the things we know. The thing we think, right, about what creates this effect is a model. And that model is that you have some star, which has a relatively old star. It's got many layers of density of different material. And what happens is that the innermost layer that's under an enormous amount of pressure starts to collapse in on itself, right? That's what these little inward going arrows are. It shrinks and shrinks and shrinks until the matter starts to collapse into each other, so it's no longer even atoms anymore, right? And as that energy sort of collapses inward, it creates a burst that explodes outwards and blows away some large fraction of the star, leaving behind a neutron star in the middle. So that's our model of what we think is happening. And the neutrinos might be able to help tell us if that's really what's happening, right? So the idea here is that the energy is sort of the same in many senses as the energy that you get from dropping a piano, say, right? The piano falls, there's some amount of gravitational potential energy there, right? And when it hits the ground, it goes into kinetic energy and explodes outwards. right? And so that's our idea of what we think is happening with a star-going supernova, right? The gravitational energy, potential energy is collapsing inwards, right? Sort of going downwards. And then that energy has to go someplace, right? It has to end up somewhere. The trouble is that it's got nowhere to go, right? You're at the center of this really dense object, and the only thing that can escape are the neutrinos. So as we were just talking about, they interact really, really weakly. And this is why when a star goes supernova, right, you get 99% of the total energy comes out as neutrinos. So remember when I was showing you this picture, and this star is bright as the whole galaxy it's containing, that brightness is less than 1% of the total energy released. The rest of it is going into the neutrinos, right? And those neutrinos are coming from right at the very center, from right where the gravitational infall is happening. So that we think they can tell us a lot about what's going on. And it turns out we don't actually know that much about what's going on, right? Like this is a nice, simple picture. But of course, we want to understand it better than that simple picture, right, of arrows coming in. We want to try and model what's really happening in the center of the star. What are the dynamics? And it turns out when you try and do that, it gets really complicated, right? So these are some pretty pictures that come from some research at Caltech. And they've been working to try and model these supernova collapses for many years. And it's only been in the last few years that they can even get the models to explode, right? And it turns out it's really hard to try and make this happen. And so we want to know, right? So they can play around with the models and try and see, did this makes the star explode, or I can make some other choices, and this makes the star explode. But what we really want to know, if we want to try and answer the question of what's really happening, is we need to know what's happening in the center of the star. And the only thing that can tell us that is the neutrinos. So we have an example of this working in practice, which is supernova 1987A, which is really exciting to us. I'm not sure it's exciting to most people. This happened in the Large Magellanic Cloud, which is about 55 kiloparsecs away. It's one of these satellite galaxies surrounding the Milky Way, right? And there's a picture of it, of the supernova, and then that little dot is the star that it originally came from. Right, it's this really bright supernova. And in this supernova, we saw the neutrinos in existing detectors. We saw about 24 of them in two detectors. Kamiokande, which is the predecessor to Super Kamiokande, and another one called IMB, which is in a salt mine in Indiana, I think, something like that. Saw these 24 neutrinos, right? And I'll tell you that this many papers, at least a year, gets published on these 24 neutrinos, right? It's since this time, right? It's a remarkable thing, but it's because this little peak, right? You see all this little peak of neutrinos showed up of relatively high energies, and then the energies got lower as we expanded over 10 seconds. This is the best information we have about what's happening on the inside of a supernova, right? And think about that too, right? This all happens in 10 seconds. This is on astronomical scales. This is literally instantaneous that this explosion happens in. Hold on. Let me come repeat your question.
How can you be sure that all of those neutrinos came from this very tiny point in the sky and are identified with that supernova?
So that's a really good question. The reason is that neutrino interactions in the detector are relatively rare, right? So we know that in the course of a day, these modern detectors are seeing 10-ish, 20-ish neutrinos a day. These detectors are seeing maybe one or two, and so to get 24 within 10 seconds was a really remarkable thing. So I don't know, maybe one of them isn't a supernova neutrino. But there's more to it too, right, which is that the energies tell us something. So these, if you look on the y-axis here, right, these energies range from about 8 MeV up to about 40 MeV, right? And we know from many years of studying the sun that those neutrinos, the highest energy solar neutrinos, are 5, 6, 8, maybe 10 MeV. So these are sort of too energetic to be coming from the sun. But they're at the same time not energetic enough to be coming from the atmosphere. Exactly right. The cosmic ray neutrinos tend to be, another order of magnitude more energetic than these. Right? So it sits in this very narrow sweet spot where we could be sure that they were coming from this supernova. And I'll say that most of these were observed via a process called inverse beta decay, right, where you reverse the beta decay of a proton. Right, and in that process, you lose the directional information. But a few of them can be observed via scattering, right, where you do get a little bit of directional information.
On your slide there, it says it was detected 2 hours before the light
Exactly.
So we're talking about the violation of nothing travels faster than light.
Excellent question. So the reason that we saw the neutrinos 2 hours earlier is because in this process, the neutrinos escape faster than the light does, right? That the neutrinos start streaming out, explode and start streaming outwards, and the light is still trapped inside this incredibly dense medium for 2 hours or more, right? I mean, the way to think about it, right, is that when this process happens, if the star is a little bit bigger, it turns into a black hole and the light doesn't escape at all. Right, so as I said, it takes many thousands of years for light to get out of the sun because the material is so dense that the light can't escape. It keeps bouncing into stuff. Right, and it's an excellent point, right, as I'll get to in a few slides, that we can use the neutrinos as an early warning system for a supernova happening somewhere in our vicinity. Right, so this discovery of the supernova neutrinos also led to a Nobel Prize back in 2002 for Ray Davis and Masatoshi Koshiba, who was the spokesperson of Kamio Kande at the time. Right. So the next time a supernova occurs, you can tell I unfortunately wrote this talk a little fast. I left out the slide saying that supernovas are really rare. Right. Supernovas in our galaxy happen somewhere between once every 30 years or once every 100 years. They happen so infrequently that we don't even have a good measure of their rate. Right. So this is a rare opportunity, and we want to be ready when the next supernova happens, because there's a lot we can learn from it, right? We can learn about the physics of the star, right? The interest of this group, right? We can learn about the physics of the neutrinos, right? There's some stuff that happens in a supernova that doesn't happen anywhere else in the universe, right? The density of neutrinos is so high that the neutrinos interact with each other. Remember, a neutrino will pass through a light year of lead. So you can imagine how many neutrinos you have to get in one place for the neutrinos to start interacting with one another. Right, and that the thing that makes all of this possible is you need to measure sort of the structure of the outgoing neutrinos, right? So what neutrino flavors and what neutrino energies happen over time as that burst occurs, right? So what we saw here, right, is you see this axis is the energy and this axis is the time. So we want to fill this in much finer detail the next time around, right? So so this is sort of an idea of what that would look like, right? If you look at this one, right, if we had a really close supernova, we could see it in very fine detail. This is telling us about the flux of these neutrino flavors, the electron, the anti-electron, and the nu mu and the nu tau, in a liquid argon type detector, right? And so what you're seeing is that you can see from this structure, right, you see this rise up as the neutrino flux starts to increase, as the matter starts to fall in, right? It gets a little denser. Then I actually don't know what causes neutrino trapping, but it creates this little kink in the spectrum, and then all of a sudden the center of the star goes through what's called neutronization, right? What that means is that process where you essentially take a bunch of individual atoms and turn them into one enormous atom. That's what a neutron star is, right? It's essentially nuclear material the size of the Earth and the mass of many times the sun, right? It's a really crazy object. But when that happens, you get this huge burst of neutrinos coming out. And you'll see that this burst only happens in the electron flavor. So it's very important to try and observe all these different flavors of neutrinos over time during the burst. Right? And so the way you do that is you have lots of different kinds of detectors around that are sensitive to different parts of that spectrum. Right? You have detectors using water, like Super Kamio Kande, and then scintillator, like I was talking about earlier in that first discovery of the neutrino. They used a detector with scintillator to try and detect it. What I'm going to talk about here is using detectors made of liquid argon to try and detect them, because it's something we're working on here at Fermilab. Right? So I mentioned this Dune experiment early on. Right? This is an experiment that essentially exists because of measurements made of solar neutrinos. Basically, people tried to do astrophysics and inadvertently discovered something about particle physics. Right? So we've built this detector primarily to do particle physics, but at the same time, it can also then contribute back to astrophysics. Right? So you've built this detector to detect the neutrinos that we make, but it can also detect the neutrinos that come from supernovas. Right? As I said, this detector will sit deep underground. It's almost a mile underground in the Homestake gold mine in South Dakota. So this detector is a liquid argon. It's called a liquid argon time projection chamber. You probably don't care about the details of what that means, but the thing to know is that it can take very detailed and precise images of the neutrino interactions as they occur. And specifically, this type of detector is very sensitive to electron neutrinos, right, which is different from most of the other detectors that are out there. The water-based detectors and the scintillator-based detectors, which are most of the detectors that are around, use this inverse beta decay reaction. And that inverse beta decay reaction happens when you have a free proton and it interacts with an anti-electron neutrino that comes into the detector. Right? That's how you reverse the beta decay process. Well, if your detector is made of just liquid argon, you don't have any free protons there, right? Argon is a noble gas, right? So the material is just argon atoms. And so instead of seeing this inverse beta decay reaction, we see an interaction of the electron neutrino with the argon atom itself. So this can tell us about that new efflux, which can tell us about the neutronization burst and that little kink in the beginning, and all those other interesting dynamics, right? So it's very important to try and make this detector sensitive to supernova neutrinos, right? And it's important because the neutrinos are on their way to us now, right? Remember, the galaxy is 650 light centuries across, right? Which means that if we have the rates right, there's about 2,000 core collapses that have already happened and have neutrinos already coming our way. Did I get my facts wrong?
Yeah, if you could go back one slide there and take a look at that detector. I see a cathode and an anode. Can you describe how that detects a neutral particle?
Absolutely. It's a great question. So the detector itself, the cathode and the anode, aren't involved in detecting the neutrino, right? As I said, we never detect the neutrino directly. What happens is the neutrino comes in, hits an argon atom, breaks up that argon atom, and produces charged particles that come out of that interaction, right? So you'll get an electron neutrino will give you an electron, a muon neutrino will give you a muon. It's what we call them, the electron neutrino and the muon neutrino. And additionally, you'll get some particles that come out of the nucleus itself. So at the energies of supernova neutrinos, typically what you'll see is a single electron and then what are called de-excitation photons. Because the supernova neutrino doesn't have enough energy to break up an argon nucleus, but it does have enough energy to excite that nucleus. And the way a nucleus de-excites is it emits photons, right, as it comes back down to the ground state. So that's what you would see, right, is a little electron. My old advisor, who helped me with this talk, used to call them crummy little stubs because they're relatively small on the scale of what you normally see in these detectors, but they're very sensitive, so we can still see them, right? And the role that the anode and the cathode plane play in this, right, is that when a charged particle passes through liquid argon, what it does is it ionizes the argon as it goes, right? So the particle comes in, neutrino breaks up a nucleus, get an electron, creates a little track of ionized argon where that electron passed through. All right, and normally what would happen is that argon acts as a scintillator, the electrons fall back down, light comes out of the argon. But if you put a really strong electric field, and so 500 volts per centimeter, is not a meaningful unit probably, but this it requires a very scary amount of voltage, right? Many thousands of volts. In some designs, as much as a million volts to try and put this field across a many meter long drift. So what this strong electric field does is it takes that track, right? So this little bit of black, as you can imagine, representing that bit of the material that got ionized by the particle, right? So this strong electric field then pulls those electrons towards the anode, right? So it just pulls the electrons away from the now argon ions, and they get collected on these wires that sit where the anode sits. And so by looking for signals on those wires, which is what you see represented here, you can reconstruct what that event looked like in space. All right? Other questions here? That was sort of a lot without a lot of slide to support it. Right, so as I said, the neutrinos are on their way to us, right? So it's important that we try and that if we see them, and if we see them, sometimes hours or a day before that supernova happens, that we tell people about them, right? So we have this system set up that we call SNOOS, right, which is the Supernova Early Warning Network, early warning system, right, where neutrinos, and actually now gravitational waves, now that we've discovered gravitational waves, if they see a signal, and more specifically, if multiple experiments see a signal at the same time, right, then it sends out an automatic alert to all the other detectors and to the telescopes on Earth saying, now is not the time to be cleaning the lenses. Turn the telescopes towards the sky and start looking around. A supernova just happened, and we're going to see it soon, right?
There's no direction,
There is. We get, in a lot of these detectors, you lose, the inverse beta decay reactions in water Cherenkov and in scintillator detectors lose the direction information. But the charge current interactions like you have in argon and the electron scattering, which you get a little bit of in water Cherenkov detectors, do have a little bit of pointing information. Now, it's not perfect, right? Because the neutrino comes in, hits the nucleus, and then the electron coming out is correlated with the direction of the incoming neutrino, but it doesn't have enough momentum for it to be perfectly lined up, right? So it comes out with some amount of angular scatter. So, if the supernova is close enough, then some of these detectors may even be able to give some little corner of the sky and say, we expect the supernova to be over here. Now, if we're only collecting, a small handful of events because the supernova is on the far side of the galaxy, then we probably don't have that pointing information. But if it's, say, Betelgeuse, which is nearby and growing, right, that were to go to have a supernova, then we could definitely point right at it. Well, right at the area around it, as you saw from the... Well, we'll find out. We'll know about it in the neutrinos first. Yeah.
Okay, in the recent gravity wave detection that we had, the gravity wave went through the Livingston, Louisiana detector first, and about 7.5 milliseconds later went through the one at Hanford, Washington. Would timing differences in these various detectors scattered around the planet, just using geometry, give us some sense of where they came from or where we might look to see the nova?
Interesting question. I don't know that anyone's tried to make that work. It's possible they could. I don't know. Other questions? All right. So let's take one step further along to even crazier stuff out there in the universe. This is, of course, an artist rendering. We can't see that. But there is stuff we can see, right? There is some really high-energy astrophysical phenomena out there, right? And the belief is that these things might be acting as cosmic accelerators, right? Taking individual particles and speeding them up to energies well beyond the stuff that we can create on Earth, right? And it's tricky to try and figure out exactly what's happening in them. So one of the ideas is this idea called the active galactic nuclei, right? This is one example of the thing that can create these very high-energy particles. There are others. And the idea here is that you've got some galaxy with a really strong black hole in the middle of it, and depending on where you're pointed at relative to the galaxy, you see less or more of the energy that's coming out of that black hole, because it accretes stuff inwards and then ejects it outwards in these two things called jets, right? So you can see you get this really high energy stuff if you're looking right at the top of it, but you get relatively low energy stuff if you're looking right at the side of it. And so the thought is maybe these things are also creating really high energy neutrinos, right? And as always, the great advantage of neutrinos is that they're neutral. So this stuff can escape from right out of the middle. And the other thing, of course, is that as the neutrinos travel between the galaxy and us, they don't get scattered by dust. They don't get bent around by magnetic fields. In principle, they could point right back at their source, if we had enough of them to overcome the fact that our direction resolution with neutrinos is pretty poor. So a question you might ask is, how do you know a neutrino it comes from an astrophysical source, right, as opposed to one from much closer by, right? And because of course the neutrino can't tell you where it's from. The way you know is that it has really, really high energy, right? There's this constant background of neutrinos that are coming from cosmic rays, so protons flying around the galaxy, interacting with the atmosphere. That's creating those neutrinos that we used in Super Kamiokande to discover neutrino oscillations. But we also know that these neutrinos can only get so high in energy. So what we're looking for is neutrinos in the PeV energy scale, right? So these are 100 billion times more energetic than the neutrinos that come out of a supernova, right? This is a whole other scale of energies we're talking about here. We aren't even close to making PeV neutrinos on Earth, right? We're making maybe GeV neutrinos, which are, even 100 million times, less energetic than this, right? It's a whole new scale of it. Right, and so the thing you're looking for, right, is that we can predict sort of the spectrum of how many atmospheric neutrinos we expect to create very high energies, and we look for an excess out above that, and so that's what you see here in these 3 points, right? Is neutrinos that are so energetic they are just super unlikely to have come from our atmosphere, right? The challenge, of course, is out here in this long tail, right? Even the extragalactic ones, or astrophysical neutrinos, are happening very rarely. So you need a really, really big detector to try and detect them, right? And it's basically impossibly expensive if we have to build that detector out of materials. So you try and look for opportunities to turn something naturally occurring into a neutrino detector. And the two examples of experiments doing this are to turn the southern polar ice cap at the South Pole into a neutrino detector. That's an experiment called IceCube. And this KM3Net experiment who's working to try and turn the Mediterranean into a neutrino detector, right? And this gives you this huge amount of mass to try and detect the neutrino in, right? So this is sort of this is looking now at IceCube, right? The thing you're looking at here, this station, sits right, is that little square right in the middle. And the detector itself is deep in the ice, well below that, and it's the space of almost a cubic kilometer, right? So you can see compared to the Eiffel Tower how big of a detector this is, right? It's really incredibly huge, right? It's sort of hard to comprehend in some ways. But the advantage of having this much mass is that it was able to see these neutrinos that were so high in energy they can't possibly have come from right around us, right? In fact, and they're rare enough that they've given them names, which is, we've called them the Muppets, right? Which is Bert, Ernie, and Big Bird, right? These are the most energetic neutrinos that we've ever seen anywhere, right? And to give you a sense of scale, like this is just a pretty picture, right, of what that neutrino looks like in that detector, right? You can see that each of these little strings here has light collectors along the way, right? And so each of these little dots corresponds to one of those detectors that we've placed in the ice, right? And to give you a sense of the scale here, here's one of those those neutrino events sitting on top of a football stadium, right? So this event is really enormous, right? The neutrino comes and interacts and just sends energy out in all directions, right? Inside the detector. Right? And so this is really exciting, right? Because we can take these neutrinos and look at where they came from. We have some pointing information and say, where do these things come from in the sky? And so that's the idea of what's happening here. We've now detected 20-ish of these so far. And we place them out in the sky, and what do we find is mostly nothing. Right? So even this little purple box is suggestive, but it's not statistically significant yet. But we're going to continue to look, right, to try and see if we can pinpoint a source that's giving us these incredibly high energy neutrinos and see if what we find there. Is there an active galactic nuclei there, something else? Where are these cosmic accelerators coming from? Right. So like I said, we haven't found anything yet, but we keep looking. So that's basically the story, right? The neutrinos are these neutral particles that interact very weakly, and that's a curse because it makes them hard to detect, but it's also a blessing, right? Because they can tell us about regions of the universe that we just don't have access to with any other observable. Right? And because they can escape these really dense regions, they can tell us about the fusion happening in the middle of stars. They can tell us about the bursts and supernovas, and maybe they can tell us about these cosmic accelerators. But of course, only if we're looking for them, which is why we keep building new detectors to try and detect them better and better. All right. Thank you.
If there's more questions, I have a microphone here for anybody.
So what's the chance of those last ones, the cosmic accelerators, just being, you're saying it's on a whole entire different scale, of being just a whole different particle or element of some sort, not a neutrino, but something else?
I think we're fairly confident that these are neutrinos, right? Because they come and they interact. So these three look, they sort of look like blobs here, right? But we can associate these particular shapes with electron or neutral current interactions. There are other ones where you can see what look like really long muon tracks that sort of cross that whole detector, right? So very similar to what you would see in another kind of particle detector, but at a much larger scale. And so, in some sense, right, if it behaves like a neutrino, it is a neutrino, right? It's the only way we have to tell. All right, so the question was, how long did it take to build IceCube, and who was responsible for building it, effectively? For running it. Yeah. Absolutely. So it took, I want to say, 6 or 7. Okay, actually, wait. We can count it up here. So 1, 2, 3, 4, 5, 6 seasons. To and a season is sort of the South Polar summer, right? My information on IceCube is somewhat limited, so I was never an IceCube collaborator. I just think it's super cool. It's a very cool experiment. It was built by a consortium of a big international collaboration. A collaboration actually that is both particle physicists and detector experts and astronomers and astrophysicists involved. It's a very sort of cross-cutting group, and it was built, sort of funded by the NSF Polar Programs. Actually, is the one who paid for a large fraction of it. Basically, the whole cost of this experiment was shipping diesel fuel to the South Pole, because the way you create these long, these 1.5 kilometer holes, right, and put the light collectors in it, right, is you just melt a column downwards and lower a string of photon detectors in, and then let it refreeze into ice, right? So it was melting out these columns of ice was most of the cost of the detector, right? And I don't know how big the collaboration is. My guess is hundreds. Yeah. Yeah, exactly. It's very, it was a real undertaking.
What's the schedule and the probability that Dune's going to be completed here?
What's the schedule and the probability? So I am very confident that we're going to build a detector in South Dakota underground. The schedule is to have the first detectors underground in the early 2020s, and to have a beam pointed at them around 2026. Current idea. I think it's 2023 is the time scale for the first detector underground operational. Right. There's I showed you a picture of these modules. Right. There's going to be 4 of these. Right. And the idea is to build them sort of in series. Right. So the first one will turn on, and then the second one will turn on, and then the beam will be pointed at them, and then we'll build the other 2. And that process will take from 2024 until 2028 or something. Mm-hmm.
Alex, if you go back to the galactic map a second.
The galactic map. Wait, where are we? This guy.
No, the other one where you showed the purplish.
Oh, yes. This guy.
Question is, in the center there, the large one now, is that one event or is that recurring events we're seeing from that area?
So these little crosses, as I understand, right, bearing in mind that I didn't make this plot. I'm not a member of the experiment that made this plot, right? These crosses correspond to candidate neutrinos, is my understanding, right? So those 3 PeV neutrinos definitely cosmological in origin or astrophysical in origin. These, right? If you come to slightly lower energies on this plot, right, you can pick up some that are likely to be astrophysical, but not guaranteed, right? But you can then look at them on the sky and say, is there a concentration of high energy neutrinos somewhere, right? And so this little purple spot is essentially telling you that these 4 happen to be nearby one another. So maybe that's a sign that there's something there. But the significance is not yet high enough to be statistically significant yet. It could just be chance still. The way to find it is to detect more of them, right? Yeah.
Is there any evidence that mass affects neutrinos, either extragalactic a la lensing or just in the field of a very massive star?
Yes, we actually know that being in a dense medium does affect how the neutrinos behave. The place we know, you don't really see lensing with neutrinos, but what you do see, it's a very interesting point. It's a little subtle, so I skipped over it at the time. Right, so if you've got neutrinos that are coming out of the sun, right, which I said that the flux of neutrinos is lower than we expect because some of them are oscillating away to different flavors. What's interesting is that all of that oscillation happens between the center of the sun and the outside of the sun. All right, and by the time it gets to the outside of the sun, the neutrinos aren't oscillating anymore. They've reached a stable mix of neutrinos, and they just come to the Earth in that state. And that's because being around lots of electrons changes the oscillation probability among the different neutrinos, right? And so what's happening is you have this. if you've studied thermodynamics, right, something called an adiabatic transition. As you go from the center of the sun, where you've got this very high mass, high density, you fall down this exponential curve of density as you go from the center out to the outside. And by having that adiabatic transition, you put the neutrinos into this. They go from starting out as sort of all electron neutrinos in the middle to this very stable mix of electron, muon, and tau neutrinos on the outside edge. And that mix, as they travel, of course, the individual neutrino will continue to oscillate, but the mix of nu e, nu mu, and nu tau all stays the same, right? And the reason that happens is because of what we call the matter effects, the MSW matter effects, named after three guys, as the neutrinos pass through. So we know that matter makes a big difference. And in fact, one of the things we're trying to study at the Dune detector here, right, is we want to look for those matter effects happening in neutrinos traveling through the Earth. Now, of course, the Earth isn't nearly as dense as the sun, so those matter effects are a lot more subtle, which is why we haven't found them yet. Yep.
You showed some neutrino detectors that are taking accelerator-produced neutrinos.
Yeah.
Right, and these like Minos or
yeah. Well, Minos not anymore. It shut down this year, but Nova is.
The question will apply to Minos and Nova and
sure.
Mini Boon and whatever. What you're mainly studying is accelerator-produced neutrinos that are passing
exactly
through
right.
these things, but I presume they have some capacity to look at neutrinos from astrophysical sources, even when the beam is off.
Sure.
And I wondered if you can say something about what experimenters do. They leave it on. They're keeping an eye on events.
Yeah.
Maybe they're not really optimal for looking at supernovas or
well,
whatever.
this is a very good question. So Minos is particularly troublesome for supernova neutrinos because there's lots of dead material on the detector. Right. Most of the mass in the Minos detectors was made out of steel. Right, so you can't see any of the interactions happening in the steel. You can only see them in the scintillator planes that sit between the steel. Now, Nova is all active. Now, by all active, I mean about 85% active, but still a much better fraction. So if a supernova were to go off, right, we will be able to see those events inside Nova. The challenge, of course, is that the Nova detector, unlike Dune or Minos, a lot of the other ones I was talking about, or Super K, is actually on the surface in northern Minnesota. Right? So it's being constantly bombarded by cosmic rays. In fact, we see 8 billion cosmic rays a day in this detector. Right? So that's a lot to try and sift through. But Nova is in the SNOOS network, right? And we are, in fact, literally today, we were having a meeting talking about getting our trigger going so that we could detect a supernova ourselves, right? If we saw a lot of low energy events happening at the same time, right, we would say, we've detected a supernova. We record those events and we send a trigger out to the SNOOS network. And then Dune, of course, is being built with supernova neutrinos in mind, right? And so beam on or beam off, it will always be looking for a supernova burst or some, a collection of neutrinos happening sort of in sequence in time that we can detect and say a supernova is happening. In fact, a lot of work's going into the data acquisition system and the triggering system so that if a supernova occurs, we definitely detect it and we definitely trigger on it and record the data. Because they're so rare, we don't want to miss one, right? Other questions? Come back in a minute. Yeah.
I assume from the discussion that you observe a track the track itself, tell me if I'm right or wrong, the track itself is not the neutrino, the track is the decay from the collision of the neutrino. Is that
exactly
correct?
Right.
Okay.
Exactly right. This is a very important point, right, which is that you never detect the neutrino itself because they're neutral, right? That all of our detection technologies rely on either light or charge. So you need to have some charge to be able to see it.
Yeah. My question was, you produce the neutrinos using accelerated particles.
Uh-huh.
What are those particles? How are they produced, and how are they accelerated?
Excellent question. So, this is more in my wheelhouse, right? About how we. So the way you make neutrinos at an accelerator, right, is the thing you accelerate is protons, right? So here at Fermilab, right, you take hydrogen, you ionize it, you get the individual protons out, you accelerate them in a linear accelerator, which is happening down here, right? Goes into a small ring, gets accelerated some more, goes into a large ring, gets accelerated even more. Oh, going the wrong way. Gets accelerated even more, so you now get these protons up to 120 GeV in energy, which is 99.9999 something. I actually don't know the number of nines. Very close to the speed of light. Then you take those particles and you pull them out of the ring and you collide them with a target. So in our case, we use graphite. You can also use beryllium. Right? There's various other materials. Take those protons, they collide with the target, and then when they collide with that target, they produce a whole spray of other particles coming out, right? Of all sorts of various kinds. But the ones we care the most about are called mesons. So a meson is a bound state of a quark and an antiquark, and they're unstable. And the lowest energy ones are called pions, pi pluses, pi minuses. And those pions decay after a certain amount of time, basically always into a muon neutrino and a muon, 99.9% of the time, something like that. And so what you do is the proton hits the target, produces a bunch of pions. Then those pions have an electric charge. So you use these things called focusing horns, right, which essentially act like big lenses to point all of those pions towards your experiment. And then you let the pions just travel in a decay pipe, which is a big volume that, well, it used to be vacuum because you didn't want the pions interacting with stuff. Now it's full of helium, so you don't have to worry about keeping it a pressure vessel, right? You let those pions decay, and because you've pointed the pions at your detector, when the pions decay, most of the neutrinos are pointed at your detector too, right? And so that's how you create a beam of neutrinos. And the fact that pions mostly decay to muon neutrinos is why long baseline neutrino experiments look for muon neutrino oscillations, muon neutrinos disappearing, or muon neutrinos becoming electron neutrinos, right? Because muon neutrinos are the convenient thing to make with a particle accelerator. Mm-hmm. Hold on. Give him 1 second for the mic.
In that chart where you had the 20 events and it showed the supernova.
Yeah.
So actually, how many neutrinos probably passed through that same detector but were not detected?
Oh, probably trillions.
Trillions.
Right.
So I'm still a bit confused. When you say you see the trail or whatever you want to call it,
yeah,
as the neutrino ionizes, it's liquid argon?
Yeah, so in liquid argon. So
a neutrino then passes through many electrons. It's just that it does not hit the nucleus then.
Yeah, so exactly right. Which is that you only ever see, the only neutrino you ever see is the neutrino that stops, hits a nucleus, and produces charged particles. Most of the neutrinos pass right through.
Well, that's why I'm confused now. The difference between ionizing the atoms of argon versus impacting the nucleus. So if it hits lots of, why aren't you detecting all of them?
So the neutrino isn't actually ionizing stuff, any of the atoms, right? Because you need to have an electromagnetic charge to be able to do that ionizing, right? So the neutrinos mostly just pass through and do nothing. Very occasionally, a neutrino hits an argon atom, produces a charged particle, and the charged particle does the ionizing.
Okay, now it's clear. All right. Thanks.
More questions?
Is that it from everybody? I guess so.
Oh, we got one more.
Oops.
Oh, I'll bring you my mic.
Do other types of supernovae, like type 1As, produce neutrinos too, and are they different from the kind you see from type 2?
Great question. So type 1 supernovas tend not to produce nearly so many neutrinos, right? I can't tell you they don't produce any, but the mechanism is pretty different, right? It happens in a type 1, right? So as I'm trying to remember the details of it, there's this very interesting idea with type 1 supernovas because they act as these sort of standard candles because you have my memory is that you have a star next to a black hole and it's pulling material away, right? And that process just doesn't produce this large burst of neutrinos all at once, right? Because this is the key, is that, you think about, when I say that 99% of the energy in the supernova goes into neutrinos, this is an unfathomable quantity of neutrinos. and then we detect 24 of them, right? So you need this enormous burst all at once to be able to detect those neutrinos. Now, it's probable that our detectors have detected neutrinos that come from supernovas. There's this thing called the relic supernova neutrino background. There's this constant flux of neutrinos coming from supernovas of various kinds, going around the universe all the time. But the rate is pretty low because neutrinos don't interact that often, right? So there are detectors being built to try and detect this specific rate, try and detect the supernova neutrino spectrum, but not from any particular supernova. But we haven't done that yet, right? You need this big burst all at once because you need that time coincidence, right? You need to know that these 24 neutrinos happened in these 10 seconds to know that they came from a supernova at this stage, right? So this sort of slow accretion process doesn't create that big burst.
You'd said earlier that in the sun, the neutrinos start out in the center as electron neutrinos.
Exactly.
And as they're going through the sun, they change into the other
flavors.
Types. Yeah. So I assume a larger star would have a different ratio because the neutrinos are going through more mass because it's larger?
So it probably wouldn't, actually. So and the reason is because the mix of flavors when you get to the outside is not a feature of the density of the star. It's a feature of the physics of the neutrino mixing, right? Which is that you get so at a sort of technical level, right? What's happening with neutrinos is you've got two different ways of looking at those three types of neutrinos, right? You could think of them as the electron, the muon, and the tau neutrino, but you can also do what's effectively a coordinate transformation into what we call nu1, nu2, and nu3, which are neutrinos that have very definite mass. It's this very weird quantum mechanical thing, right? Which is that the neutrino of a particular flavor doesn't have a well-defined mass, and a neutrino of a particular mass doesn't have a well-defined flavor. What you have is that a neutrino of a particular flavor has a mix of masses in some ratio, right? And a neutrino of a particular mass has a mix of flavors in some ratio. So what's happening in the sun, or in any star, right, is in the middle you start in a pure electron neutrino state, and as you do that adiabatic transition from the center to the outside, you rotate from an electron neutrino state into a nu1 state, right? So that's why it doesn't oscillate anymore, because it's all nu1. But when a nu1 reaches your detector, you've got, say, a 60% chance of seeing a nu e, 20% chance of seeing a nu mu, and a 20% chance of seeing a nu tau. But it's not oscillating anymore because it's already a nu1. It can't change to anything else. So if your star is bigger and denser, as long as you have that adiabatic transition down that exponential curve, I think you'll end up with the same state at the outside edge, no matter how big the star was.
Got one more over here.
Yep.
Maybe I just don't understand the standard model well enough, but
it's all right.
This is a particle, right? So does it have a carrier that is that I don't even know if I'm phrasing that question properly.
So I think I know what you're getting at. Hold on.
And how does it deal with like Higgs boson and all that kind of fun stuff?
Sure. So these are leptons, the part of the standard model they fall into. So what lepton means is it doesn't interact. So the leptons don't interact via the strong nuclear force, right? So the gluon here is the force carrier for the strong nuclear force. Doesn't interact with the neutrinos. The photon is the force carrier of the electromagnetic force, right? And we know it doesn't interact with that because they're neutral, right? So that's what having a charge means, is you have a charge for the electromagnetic force. The only force carriers that these interact with are the W and the Z, which are the force carriers of the weak nuclear force. And the reason that it's weak is that this is massless and this is massless, and these have relatively high masses, right? So they're very short range and very weak because of that, right? And then we know that they have mass, so that we know they must interact with the Higgs boson at some level, but they are so much less massive than the other particles in the standard model that those couplings are very, very small. In fact, the idea is that the mechanism in the model that gives the neutrinos mass is believed to be different from the one that gives the other particles mass because it's so small that you have to invent this new mechanism. Otherwise, you have this very unnaturally tiny coupling between the Higgs and the neutrino. So it doesn't. Well, yes, but what it suggests is that there are 3 more neutrinos that are very, very heavy that are the partners to the 3 light neutrinos. You have this thing that gets called the seesaw mechanism, which is that the heavy ones are so heavy they make the light ones really light. It sounds crazy, but that's actually the model. Yeah.
So do
sure.
neutrinos ever stop? You say they keep basically going.
Yeah. So if a neutrino interacts with the nucleus, there's often no neutrino anymore, right? The interaction is that a neutrino comes in, you got a neutrino and a nucleus, right? And what comes out the other end is a different nucleus and the charged partner of the neutrino, right? Basically, the neutrino comes in, exchanges a W with that particle, and the neutrino is gone, and you have an electron on the other side. Because you have to conserve lepton number in that interaction, so the nu e becomes an e, or a nu mu becomes a mu.
Well, if that's it on the questions, then thank you very much, Alex. We appreciate it.
Of course.